Today we're going to be looking at analyzing antiderivatives graphically. So we're going to use the fundamental theorem of calculus to figure some things out. So first, here's this graph. This is the graph of f, okay? And so we got to go through and read and understand what all of this is telling us, this whole like paragraph right here. So the graph of a continuous function f with domain 0 to 8 is shown above. So this is f. It's continuous from 0 to 8. So that's 8 right there. Let h be the function defined by h of x is equal to the integral from 1 to x of f of t dt. All right, so h of x is the integral of this function f right here. The graph f has horizontal tangents at x equals 1, x equals 3, and x equals 6. So what we're going to do is we're going to draw horizontal tangents, all right? So right here at x equals 1, which is right here, we have a horizontal tangent. So I know the tangent line is 0, right? The derivative is 0 right there. Also at x equals 3. So right here we have a horizontal tangent line. And then at x equals 6. So right here at 6, we have a horizontal tangent, okay? The areas of the regions bounded by the x-axis and the graph of f on the interval 0 to 1, so 0 to 1, 1 to 4, so 1 to 4, and 4 to 8, are 2, 4, and 12 respectively. Now, what the respectively means is that they're in order. So 0 to 1, that area, that region right there is area 2. So this we know has area equal to 2. And from 1 to 4, that's the second one. This is the second one here. So it's the second one here. So 4. So this area is 4. And then and 12 from 4 to 8, the area is 12. So this area right here is, let me just put 12 here. All right, so that's everything it tells me. Okay, so a few other things that I know is h of x is equal to the integral from 1 to x f of t dt. Okay, because it's an integral function and it ends in x, I can take the derivative. So that would mean h prime of x is equal to f of x. That's the fundamental theorem of calculus. Well, what happens if I take the derivative of this? Well, I have to take the derivative of both sides. So that would mean that h double prime of x is equal to f prime of x. So what we're looking at is the graph of f, but it's also the graph of the derivative of h. Okay, so this goes along with some stuff that I taught you before, right, in Unit 5. Okay, so here we go. Let's answer some questions. So what is, I want us to be able to find h of 1. So that's the integral. So h of 1 would be equal to the integral from 1 to 1 of f of t dt. Well, what do I know? The integral from 1 to 1, well, that's 0. So that means h of 1 is equal to 0. So now we know a value, right? H of 1 is 0. Okay, what is h of 0? Well, h of 0 is equal to the integral from 1 to 0 f of t dt. The order is wrong here. So integral property says, okay, I can switch the order, but I would have to put a negative in front. So this is equal to negative the integral from 0 to 1 of f of t dt. Okay, so this is equal to negative, and then the integral from 0 to 1. Well, we know this is above the x-axis, right? So the area and the integral are the same. And since the area is 2, the integral is 2. So that means h of 0 is negative 2. All right, and that's kind of how you do these problems, all right? Okay, so I'm going to switch. I'm going to come back to talking about this graph. I'm going to be coming back and forth because when we switch the page, I still need this graph, okay, and the information that I wrote. So for this, I want to find the value of x for which h of x is a maximum. Now, we're just saying maximum, and we have to remember that when I say when is it a maximum, that would mean an absolute maximum. So the biggest one, right? So whenever I say maximum, they're asking, or anybody, when they say just maximum, they mean absolute maximum. Okay. So this, if you go back to the graph, okay, in our function, this is a closed interval from 0 to 8. So we can use the candidates test or the closed interval test. So we have to find, okay, the endpoints. So the endpoints were x equals 0 and x equals 8. And then we have to find the critical numbers, okay, or the critical values. And the critical values are when h prime, because we're looking for h, so when h prime of x is equal to 0, or when h prime of x is undefined, right? So either one of those. All right, so we got to write this. We have to write this. You guys didn't do this when we took the test on this. You got to write this, okay, both these. All right, so where's h prime? How do we know when h prime? So h prime of x is the same as f of x. So if you look at this graph, okay, f of x is 0 at 1, 4, and at 8. So that means that the derivative is 0 at x equals 1, x equals 4, and x equals 8. Okay, where it's undefined would be where there's a corner or a cusp or anything like, well, we don't have any of those, right? So this is never. Okay, so the next thing we got to do is we gotta use the endpoints, okay, and we're gonna find, all right, which one's the largest, right? So we got to find h of 0, we got to find h of 8, we got to find h of 1 and h of 4, okay? So h of 0, okay? Well, from the first page, right, we got h of 0. H of 0 is this value of -2. So I already calculated that, so we don't need to calculate it again. H of 1, I calculated that on the first page also, right? And h of 1 is 0. All right. And then h of 4. Okay. So h of 4 would be the integral from 1 to 4 of f of t dt. Okay. So from 1 to 4, okay, that would be from 1 to 4, that would be this. The area is 4, so the integral and the area are the same since it's above. So this is equal to 4. And then I need to do h of 8. And h of 8 would be the integral from 1 to 4 of f of t dt. So from looking at this, okay, from 1 to 8, I know from 1 to 4 is 4, so that's going to be positive 4. And then from 4 to 8, it's going to be negative 12. So this is going to be 4 minus 12, which is negative 8. Okay, so I was asking for the biggest one, right? And so the biggest one is of these is 4. All right, so the biggest one is 4, and it's happening at x equals 4. So we would say h of x has a maximum of, so this is the maximum right here. It's 4, maximum of 4 at, and it's occurring at x equals 4. Okay, so keep in mind, this is the maximum value. This is where it's happening. They just happen to be the same value, right? They're both a 4. Okay. So next part is, okay, we can use the same idea right here, right? We don't need to rewrite it all over again. Okay. Find the value of x for which h of x is a minimum. Now, when I say minimum like this, I mean absolute minimum. Okay. And so when I say absolute minimum, we would need the endpoints like we did up here. We need the critical values like we did here. And then we would need to evaluate each one. And now, instead of looking for the biggest one like we did in part C, we're looking for the smallest one. Okay. So the smallest one is going to be negative 8. So we would just say h of x has an absolute minimum, or you could just say minimum, of -8 at x equals 8. And that would be the answer to that question. So for this one, we want to find the x-coordinates of all points of inflection of the graph of y equals h of x, okay? So points of inflection happen when h double prime of x changes from positive to negative or negative to positive, or when they change signs, okay? So we need to take a look at, well, let me say this. So let's point to points of inflection. This is going to happen when h double prime of x changes signs. Okay, so we want to figure out where is h double prime of x equal to 0, and also where it's undefined. Okay, it's not going to be undefined anywhere. Okay, but really h double prime of x, remember from the first page, h double prime of x is really f prime of x. So we're also looking for where f prime of x is equal to 0. And so when does that happen? Well, it's if we're looking at the graph of f, that's where we have these horizontal tangents, right? Because this is the graph of f. When f prime is 0, that would be at x equals 1, at x equals 3, and at x equals 1, at x equals 3, and also at x equals 6 right here. Okay, because that's where f prime is 0. Okay, so this is going to happen. The critical values are x equals 1, x equals 3, and x equals 6. Okay, and are they changing signs at x equals 1? Well, if you take a look at it, before x equals 1, the slopes are negative, and after they're positive, right? So that means h double prime changed signs. Okay, now how do we know these slopes are negative? It's because f is decreasing, okay, and then increasing. Here, right before 3, the slopes are all positive. After 3, they're negative. So it changed signs again at 3. And then at 6, it changed signs because before 6, they're negative. After 6, they're positive. And how do we know that they're changing signs? It's what about f? Because we got to refer back to f. It's because f is changing from decreasing to increasing that we know it's changing signs. Okay? So we would say h of x has a point of inflection at x equals 1. Okay, and it's because h double prime changes signs, but what is it about h double prime? It's f prime, but we have the graph of f, and the graph, what is it about the graph of f that's telling me f prime is changing, h double prime is changing signs? Okay, it's because f is changing from decreasing to increasing. Okay, so h of x has a point of inflection at x equals 1 because f changes from decreasing to increasing at x equals 1. Okay. At 3, h of x has a point of inflection. So h of x has a point of inflection at x equals 3 because h double prime changes signs. But how do you know h double prime changes signs? It's because f prime is changing signs. And how do we know f prime is changing signs? It's because f is changing from increasing to decreasing. Okay, so h of x has a point of inflection at x equals 3 because f changes from increasing to decreasing at x equals 3. And then we have one more. Okay, so h of x has a point of inflection at x equals 6 because, and it's about, okay, so h double prime of x changes signs at 6. Okay, so how do we know it's changing signs? It's because f prime is changing signs, because h double prime and f prime are the same thing. Okay, so h double prime is changing signs, f prime is changing signs. How do I know f prime is changing signs? It's because f is changing from decreasing to increasing at x equals 6. So because f changes from decreasing to increasing at x equals 6. And that's the points of inflection, okay? There's 3 of them for h of x. Okay, let's go to the next problem. So now we move on to another similar problem that we just that we're going to look at, and this is going to be going into particle motion and all of that. Okay, so particle moves along the coordinate axis. Position s of t is an integral function again, right? And its output is in centimeters, where f is a function whose graph is shown above with domain 0 to 8. So our position function is the integral from 0 to t of f of x dx. Notice it's ending at t because that's the input variable here. And so we're allowed to use x for here and our dx here. So we're going to go from 0 to 8 again. The graph of f has a horizontal tangent at x equals 6. So right here at x equals 6, right, the derivative of f would be 0 right there because we have a horizontal tangent. And the areas of the regions bounded by the x-axis and the graph of f on the intervals 3 to 4, 4 to 7, and 7 to 8 are 2.3. So right here, because it's curving, we're not going to be able to figure it out without being told. This right here is 2.3. So the area is 2.3. And then the area from 4 to 7, so from 4 to 7, the area is 8. So we know this is area is 8. And then from 7 to 8, which is this last part right here, is 5.3. So I'm going to drop a dash line straight down here. And I know that this area is 5.3. So we can, and then over here, all right, if you look at this, we can break this up. This is a nice line. So we could break this up into like a rectangle and a triangle if we need to, okay? All right, so a few things that we know, okay, s of t, the position, right? S of t is equal to the integral, okay, from 0 to t, f of x. Okay, so when we talk about, particle motion, we want to look at the velocity and also the acceleration a lot of times, right? So what is the derivative of this? Well, s prime of t would be equal to, okay, and that this would just be the derivative of this would be f of t. But the s prime of t is also equal to the velocity. So we also know that v of t is equal to f of t because s prime of t and v of t are the same thing. All right, what if we take the second derivative? Okay, so if we take the second derivative of t, that would be f prime of t. And so the second derivative position would be the acceleration. So a of t is equal to f prime of t. So all that said, the velocity, we're looking at the velocity function. And if you look at slopes on this, then you're looking at acceleration. So the slopes on here tell me the acceleration. So right in here, all the slopes are negative. So that would mean that the acceleration is negative in here. And here the acceleration is positive and so on, okay? All right, so I'm just going to slide this up and let's answer these first two questions. Okay, so what is the particle's position at t equals 0? So that would be s of 0. And so that's equal to the integral from 0 to 0 of f of x dx. Since we're integrating starting at 0 and ending at 0, we should know that that is 0. So now we know s of 0 is equal to 0. So it's starting at the origin, okay? And then next one is, what is the particle's position at t equals 3? So that would be s of 3, and that would be the integral from 0 to 3, f of t, sorry, not f of t, f of x, because we can use just f of x here, f of x dx. Okay, we got to find the integral from 0 to 3. Well, I know it's going to be positive, all right? So here, I'm just going to use geometric shapes to get the area. So going straight across, I know this height right here is 5 because of this y coordinate. So I'm going to go straight across here. So this area of the rectangle would be 3 times 5. This isn't drawn to scale at all, so it looks like this way is longer than this one, but this is 3 by the numbers. This is 3 and this is 5. So down here, this would be 3 times 5. And then we need to add the triangle up here. So that'd be 1/2. The base would be 3. And the height, we're going to go from 5 to 8. So the height would also be 3. Okay, so cleaning this up, this would be 15 plus 9/2. So we can change the 15 to 30/2 plus 9/2. So that would give you 39/2. And that's the position at t equals 3. All right. So I'm going to refer back to this graph and these 3 statements right here, okay, to answer the more questions on the next page. So for this first question, we want to know, what is the particle's velocity at t equals 6? So that would be v of 6, which we know is s prime at 6, which we also know is f of 6. So all of these are the same value, okay? So f of 6, okay, we just look on our graph, and right here is 6, and this is the graph of f, and so it's been labeled for us, right? So that means it's -4. So this is -4. So this next question is asking, okay, when is the acceleration 0? So that would be a of t is equal to 0. Well, how do we know when a of t is equal to 0? Okay, that would be when s double prime of t equals 0, or f prime of t is equal to 0. So that's the derivative, right? And we know that the derivative is 0, right? The derivative is 0 when we have a horizontal tangent. So if you look, the only place we have a horizontal tangent is right here at 6. So that means this is going to happen when t equals 6, because we know that f prime of 6 is equal to 0. All right, let's do the next problem. So what time during the first 8 seconds does s have its largest value, right? It's asking, when is it a maximum, right? So largest value is a maximum, right? So to do that, we have to look at the derivative of s, and we have to figure out, where is s prime of t equal to 0? Okay, so s prime of t is, what are we looking at for the graph? S prime of t is f of t, right? So we're also looking at, where is f of t equal to 0? And that will tell me where s prime of t is equal to 0. Those are our critical values. And so f of t is equal to 0 at t equals 4 and also t equals 7. So this is going to happen at t equals 4 and t equals 7. Now, we're looking for the max, so we also have to include, because this is a closed interval, our endpoints. So these are critical values, but we also have to include t equals 0 and also t equals 8, because the maximum can happen at the endpoints or at a critical value. So now what we're going to do is we're going to go through and we're going to find each of these. Now, some of these we've actually already found, okay? So s of 0, we got to find. Okay, and we're just going to look and see which one's the largest now. Okay, so S of 0 is the integral from, well, actually we already calculated it, right, in the first part. So we don't have to do the integral again. We've already calculated it. Once you calculate a value, you don't have to recalculate it on another part. Okay, so we know this is 0. We also need, that's that endpoint. We need to do S of 4. So S of 4 is equal to the integral from 0 to 4 of f of x dx. Okay, so from 0 to 4, well, I know 0 to 3 is this 39 halves. So I can just take that 39 halves, and add to it the part that's from 3 to 4. And so from 3 to 4, I know that area is 2.3. So plus 2.3. And 39 halves is actually 18.5 plus 2.3. I take that back. That's not 18.5, that's 19.5. 19.5. So 19.5 plus 2.3 is 21.8. So we know the position at 4 is 21.8, and then we need to find S of 7, which is the integral from 0 to 7 of f of x dx. Well, okay, I can go from 0 to 4. I know 0 to 4 is 21.8. And so all I need to do is go from 4 to 7. And from 4 to 7, because the region is below the x-axis, we're going to have to subtract 8. So minus 8. Okay. And then 21.8 minus 8, or 21.8 minus 8 gives you 13.8. And then we need to find S of 8. So S of 8 is equal to the integral from 0 to 8 of f of x dx, which is we can do the one from 0 to 7, which we know is 13.8, and then just add on the parts from 7 to 8. Okay, so from 7 to 8, we know that area is 5.3. So I'm going to add 5.3 to this. So this turns out to be 19.1. So if you look at these, okay, so which one's the largest, right? And the largest one is going to happen at 21.8. So S has its largest value of 21.8 at t equals 4. So S has its largest value of 21.8 at t equals 4. So the next question is, okay, when is the particle moving towards the origin, away from the origin? So this is some review of some stuff that we've covered, okay? So how do you know if you're moving towards the origin? Okay, so it all has to do with the sign of your velocity, okay, and also your acceleration, or not acceleration, sorry, your velocity and your position, okay? So the next question is, when is the particle moving towards the origin and away from the origin? So it all depends on what side of the origin the particle is on, okay? So if you're on the positive side, okay, and you have positive velocity, that means like you're on the right-hand side and you're moving right. So you'd be moving away from the origin. Okay, so to move towards the origin, the position and the velocity have to be opposite signs, okay? So if you take a look at our graph, okay, let's start out, okay, when is the position positive, okay, and when is it negative? So if you look at this, okay, we're accumulating because at position 0, we're at 0, right? Because we start integrating at 0. If we go across here, this is all going to be positive. So we're always going to be like on the right-hand side. Position is always going to be positive, okay? And so if you look at integral from 0 to 4, right, that's accumulating all this positive area. So we have 21.8. We've accumulated up to 21.8 right here. This now, when we start moving over here, we're going to start removing position, right? Because this is going to be negative. So this is positive position. This is negative position, but we're removing it, right? But we're not going to remove as much as we've added, because at time 0, we're at 0. So we've accumulated all this positive, but we're not going to add, we're not going to take away enough to get us on the other side of the origin. So really, by looking at this, S of t is always going to be positive, okay? So for this, S of t, and that is going to make this easier, is greater than 0 for, or on, for 0 less than or equal to t less than or equal to 8. So we know the entire time our position is positive. We're on the right-hand side. So now it's a matter of looking at the velocity. If we're on the right-hand side, if we're moving towards the origin, if we're on the right-hand side, we'd have to be moving left. So our velocity would have to be negative. Okay, so our velocity is our function. So where's our function f? Negative. Well, it's between 4 and 7. It's negative. So between 4 and 7, the position is positive, but the velocity is negative. Therefore, we're moving towards the origin. Okay. So the particle, and this is the hardest one of all of these. Okay, the particle is moving towards the origin for, or on. Let me change it to on, because then we can write an interval notation. On parenthesis 4, 7. All right, so between 4 and 7, I know my position is positive and my velocity is negative. I know my velocity is negative because my velocity is f of t, okay? The particle is moving towards the origin on 4 to 7 because s of t is greater than 0 and f of t, which is equal to v of t, is less than 0. So the position is positive, but the velocity is negative, okay, on 4 to 7. So how do we know we're moving away from the origin? Well, if the position is positive, which it's always going to be positive, that's going to be when the velocity is greater than 0, okay? So the particle is moving away from the origin on, okay, so position at 0 is 0, and the velocity, which is f, is positive. So at time 0, it's not moving away from the origin, but just after it, it is, okay? And all the way until 4, but then the velocity is not positive there. Okay, the velocity is 0 at 4. So now we know, okay, so it's going to be between 0 and 4. Both my position is positive and my velocity is positive. Okay, so the particle's moving away from the origin on 0 to 4, and it's also happening from 7 to 8, including 8 because the position is positive at 8. Okay, so and 7 to 8, including 8, because s of t is greater than 0 and f of t, which equals v of t, is greater than 0 on 7 to 8, including, period there too. Okay, so you know you're moving towards the origin when the position and velocity are opposite signs, okay? And you know you're moving away from the origin when the velocity and position are the same sign. And because of this, we know that the position is always positive. So really what dictates this for this particular problem is that it's when the velocity is either negative or when it's positive, okay? All right, guys. So let's go to the next problem. The next question is really kind of a do-over, okay? And it's just on what side of the origin does the particle lie at time t equals 8? So that's just asking what is the position at t equals 8, right? So s of 8 is equal, well, we calculated s of 8 right up here, right? S of 8 is 19.1. So we don't need to recalculate it. So s of 8 is equal to 19.1. And so at t equals 8, what side is on? Well, since that position is positive, we're on the positive side of the origin, okay? So at t equals 8, the particle is on the positive side of the origin. And its position is 19.1. All right, and that's how you do these problems, okay? It's just reading and realizing, okay, you're actually looking, if you're looking at an integral function and you're looking at the graph of the integrand, then that means you're actually looking at a derivative graph, okay?